Hello everyone. Our project is underwater image enhancement. So here we have, first of all, we'll see the requirement and need for the underwater image enhancement. So as we all know, the underwater imaging is becoming more and more relevant because there are many minerals and resources available in the oceans. And so this is the need for image enhancement. And in order to study the aquatic life too, there is a requirement for underwater image enhancements. So we'll see some of the methods that we have implemented here. So before going into the implementation of the methods, let us see the evaluation matrices that we have used to measure the enhanced images. So here we have used peak signal to noise ratio and the structural similarity index. So this is PSNRB. So this is the function which gives us the signal to noise ratio between the original image, which is the ground truth image, and the processed image. So here, if you see, this computes the mean square error between the ground truth image and the reference images, and it calculates the noise level in the processed image, and thus this function adds the noise to the mean square error, and finally returns the peak signal to noise ratio. And coming here, this is the structural similarity index. So it also measures the similarity between the ground truth and the processed image. So generally this is used for to compare what is the similarity between the two images, taking into account the luminance, contrast, and the structural differences. So here we'll be calculating the two constants, C1 and C2, so which gives us these are known as the weighting constants. So it is based on the maximum pixel values in the original and the processed image. So based on these weightages, we'll find SSIM, which is structural similarity index, and the contrast similarity, and we'll return it. So here we have used a model of colorization of image. So the link of this has been given in the report. So here we have taken the pre-trained model, which takes uncolored images, because in the project there was a requirement, because our results were in the grayscale image. So in order to colorize it, we have used this model. This function is defined here. And here if you see colorization, the main idea was that first of all it converts all the training images from RGB color space to lab color space. So here lab means L stands for the intensity and the lightness, and A stands for green red combination of the colors, and B stands for blue yellow color combination of the colors. So here the L, which is of black and white images, is given as an input to the neural network to predict AB channels, which are colored channels. So after that we will be combining L and AB channels to form lab images, and after that we will be converting back into the RGB images. So this is the whole code which uses the colored images after giving it input as a grayscale image. So now we'll implement, so as I told earlier, we have divided our project into three parts: spatial domain and frequency domain and some other advanced techniques. So in spatial domain, so we'll see what are the methods of filters we have implemented. So first, blur and sharpen filter. First method is blur and sharpen filter. We have implemented it. So here we have made a custom filter. It is 3x3 matrix, which is of 1. So this just blurs the filter, and in sharpen filter it is more or like an Laplacian filter. So it takes it is a customized one by setting values as 0, -1, 0, -1, 5, -1, 0, -1, 0. So this is used in order to enhance and blur the image, so that we can see what is the changes that we have got in the original image. So from here my friend Rahul will take on and walk you through other methods that we have implemented in spatial and frequency domains.
So as Vamsi has stated, the matrices which are being used to analyze the images, in this blur filter and sharpen filter, we have seen the result like the original image, and we are getting the PNSR and SSIM values. So we are looking for the values which are highest in both the cases. That will give us the most enhanced image. So we will implement this code as well. So yeah, these are the results exactly what we were getting before. So now coming to the next method, that is histogram equalization. In histogram equalization, we first convert the image to RGB color space using the CVT color function. After that, we convert the image to grayscale using the CVT color function again. This time to convert the BGR to grayscale. Then we calculate the histogram of pixel intensity using numpy histogram function. Next, we calculate the cumulative sum of histogram using numpy histogram function. Yeah. We calculate the cumulative of the histogram values and normalize them. Finally, we plot the histogram using matplotlib function, that is this. And yeah, so we'll implement this code as well. So yeah, these are the result, and this is the histogram we are getting. Then using this function, uh, histogram equalization in this code to get the result and all the matrices. Let's run this code. Yeah, so this is the histogram after equalization, and this is the resulted image. We have also used the colorization also in this to get the colored image of our output. Yeah. So coming to the next filter, that is Clahe filter. In this we have performed a contrast limited adaptive histogram equalization, that is Clahe, on the grayscale image using OpenCV create Clahe function. And then this technique improves the image local contrast, making it appear sharper and more detailed. After that, we have passed the enhanced grayscale image to the function called colorization. That's what we are doing from in every code, which produces a colored version of the image. Okay. And we have created the histogram again and enhanced of a grayscale image and normalized it and displayed the result. So implementing the code. Yeah, so this is our output image and the clay histogram is over here, so we will also implement this. Yeah, this is the histogram we are getting. Coming to the next filter, that is Laplacian filter. The Laplacian filter takes an image as an input and applies the Laplacian filter to it. And this is a simple matrices which we have used, in which the -4 is in between of the image and all the ones at its above and sideways. The function then applies the filter to the input image provided by the OpenCV, that is filter 2D. And the next step is to enhance the edges by adding them back to the original image. This is done by multiplying the image by scalar value and then adding to its original image. The scalar value is set to -1 in this code, but it can be adjusted to control the strength of the effect. Yeah. Finally, the output has been shown in here, and the matrices, that is PNSR values and SSIM. These are the output which we are getting. Now coming back to the high boost filter, here also we are using the unsharp filter function. First we are unsharpening the filter, that is unsharp mask to the input image, which sharpens the edges by subtracting a blurred version of the image from the original image, and then converting the image to to RGB, BGR to RGB, and then applying the function that is axis extensions, which is the function that extends the image borders to avoid artifacts during the filtering. And this is we are doing in all the codes, that is the matrices, that the evaluation matrices. So we are not going to explain it every time. Okay. And then plotting the results. Yeah. So we will implement this code as well. So here's the original image and the output image as well. Yeah. So coming to the next filter, that is bilateral filter. First we should know about what is bilateral filter. Bilateral filtering is a non-linear edge preserving smoothing filter that reduces noise while keeping edges sharp. It's particularly useful for the images with texture and fine details. So we use the CV2 dot bilateral filter image, which takes the image as well as these three input arguments. That is the input image, the diameter of each pixel neighborhood, the standard deviation of the color space, and the deviation of the coordinate space. These parameters control the size of filter window and degree of smoothing. Next, we convert this image from BGR to RGB and applying the bilateral filter to that and calculating the evaluation matrices and generating the output. So, yeah, implementing. Yeah. So, this is the output image after using bilateral filter. Coming to the next method, that is Laplacian pyramid. So yeah, it is a method. First we have to know what is Laplacian pyramid. We are using level 8 here. It can be changed to any number depending upon your need. Yeah. So what is Laplacian pyramid? Laplacian pyramid is a sequence of images where each level is obtained by subtracting the unsampled version of previous level from downsampled version of current level. The resulting image are the high frequency components of the original image at different scales. So now we can apply the filter to each level of the pyramid. Yeah, this is generating the pyramid of images, and we will apply the filter to each level of that pyramid, such as sharpening filter, and then we will reconstruct the image from the filtered pyramid. Yeah, and then implementing this code. Yeah, and resizing both the images and calculating the evaluation matrices, the results we are getting. And this is the image original, and this is the output image after applying Laplacian pyramid. So now coming to the next major domain, that is frequency domain filtering, importing all the necessary libraries. Then we have defined three functions over here, that is spatial to frequency, Laplacian filter, and convolution. This function will just convert the image into the frequency domain. This is the Laplacian filter applied to that frequency domain image, and it is used to convolve the image with the filter. Yeah. So coming to the first method, that is the ideal low pass and high pass filter. Here we have defined the ideal low pass pass filter function, that is this and this. In ideal low pass filter, only low frequency components are passed and high frequency components are attenuated, and just opposite of that in ideal high pass filtering, it attenuates the low frequency components and passes only the high frequency components. As you can see, there is this d naught, that is the threshold value after which it will attenuates the frequencies. Yeah, so these are the two functions which we have used for that high pass and low pass filters, and convolving that filters with the images which are in the frequency domain and colorizing those images. Yeah, so implementing that function and using those function over here, simply converting from BGR to RBG both the images and converting it to frequency domain, and then using the low pass filter and convolving with the image high pass filter and convolving with that filter, and calculating those evaluation matrices over here and the results which we are getting, like implementing the code. So yeah, this is the result which we are getting, the output filter image using the low pass filter and output filter image using the high pass filter. Similarly, we have used this Butterworth high pass and low pass filter. The only difference between that ideal high pass low pass filter is the change in the frequency responses. That is the only difference over here in Butterworth high pass low pass filter. And all the things are same as done in the previous step, that is converting from spatial to frequency domain applying those filters and convolving with them and calculating the evaluation matrices. So the results which we are getting. Yeah, so this is the low pass filter using the Butterworth high pass, and using the Butterworth low pass filter and Butterworth high pass filter, that is, these are the output images and the evaluation matrices values over here. Yeah. So coming to the next method, that is also similar to previous two methods, that is Gaussian low pass and high pass filter. This is here also the frequency responses are different in both the cases, and usually convolving with that image and applying those functions, yeah, and calculating those values. Yeah. So implementing this function. So these are the result after applying the low pass Gaussian filter and high pass Gaussian filter in the frequency domain. So from homomorphic filter, Vamsi will be continuing to explain the code.
So now coming to the homomorphic filter method. So the basic idea of the homomorphic filter is like it is a filter that uses logarithmic transformations in order to enhance the contrast of the image by adjusting the frequency spectrum. So it basically it works this way. So it separates frequency spectrum of an image into two, that is high frequency spectrum and the low frequency spectrum, and then it applies different levels of filtering to the each components. And here by adjusting the filter parameters, so we can enhance the contrast of different components of the image, so leading to the overall enhancement of the image. So here we have calculated the, as we have seen earlier, peak signal to noise ratio and spectral similarity index. So we can see this, the output by just running the code. And so now coming, this we can see this, the PSNR we have got is 16.779 and SSIM of 0.547. So now coming to another method, that is wavelet transform. So here in wavelet transform, the basic idea is here we decompose the image into different frequency subregions. So basic idea behind the wavelet transform is also to analyze an image at multiple scales of the frequency. So by different multiple scales of the frequency, we'll apply different filters at different multiple scales of the frequency, and using this process, we'll enhance some certain features of the image and suppress some unwanted features of the image. And so now we can, by implementation of the code, we can see the results that we have got. So this is the output result which we have got. So this is the end of the frequency domain filters that we have implemented in this project. So now we have tried some other methods, which is of hybrid methods, which we can say, like denoising of the image and neural networks. So now coming back to the denoising image, so it is an amalgamation, which we can say, of Gaussian filter and the median filter. So it takes advantage of both the filters in order to enhance the original image. So the Gaussian filter is used to smoothen the image, and it removes the high frequency component. So this function which I have defined over here, the denoise function, is what it does. And the median filter, it just removes the salt and pepper noise in the image. The sigma estimation function, the line which I have written over here, this is used to estimate the noise level in the image. So based on this, we'll apply this denoise NL means inbuilt function. So what it does basically is denoises the images. So the basic fundamental is that it takes the filtered image, that is Gaussian and median filtered image, and by tweaking the parameters, it denoises the images, and it converts back to the byte format of the image and returns the image. So this is what we have implemented over here. By running this code, we can see the output. So one more thing, what we have done over here is, so in order to try some new things, what we have done is we have taken the output of the histogram equalization that is done in the previous steps. So we have taken that as an input to our denoise filter. So this is the output. So we have seen the maximum better results in this version of the implementation. And meanwhile, we have taken the ideal low pass filter in the frequency domain as an output, and given that as an input to the denoise filter. So by implementing that, we can see the result. So this is the result. So we have found that in overall as a implemented methods, the histogram equalized output, which is given as an input to our denoise filter, has shown the drastic change. We can say the enhanced version of the underwater image. And now coming to the last method which we have implemented is the neural network method. So this we try to implement using autoencoders. So this part of the code is what it reads the images that were given, and here I have divided that images into train and test. So this first model is what it is an autoencoder, and this one is in a decoder. So encoder and decoder of the system. So as we all know, the autoencoder is a type of ANN that learns efficiently to encode and compress the data, and this decoder reconstructs the original input from the compressed representation. So the encoder network receives input data and compresses it by extracting only the important features from it, and whereas the decoder network will then take these features as an input and try to reconstruct the original image better way, what we can say it as an enhanced way. So by running it, we are setting the parameters for that, and we can see the model summary, which we have set it to 64 cross 64, 3. That is this is the input size we are taking into the model, and so now we are training at the model. It may take some time because as we have set it for 50 epochs. Okay, so the model has trained now. Now we can see the shape of the test. That is, there are 3 images in the test set, and the size of them is 64, 64, and 3 is for the channels. So now we are giving them as input in order to predict the model. So we have plotted the results, which we can see over here using this plot function. So this is the test image, and this is the enhanced version of this image. So what we have found is that because of the lack of the training image dataset, the model was able to generalize the input, so which resulted in poor enhancement of the system. So this is what the methods that we have trained in order to enhance the underwater image. So finally, what we have found in our result is in the spatial domain, if you go back to the spatial domain, the histogram equalized output was the one which has given a good amount of enhancement when compared to other methods which we have implemented. So this is the one which has good PSNR and SSIM. And in frequency domain, when we come, so ideal low pass and high pass filter has given us a good amount of enhancement, that is 25.664 and SSIM. And by combining this, which we have implemented in denoise filter, has also shown us some better promising results to the image enhancement techniques. These things we have been reported in the report too. So in future, what we are thinking to implement is we can switch some of the modifications, like you can use some DCNNs, those are deep convolution neural networks, to enhance the image quality, and GANs, generative adversarial networks, which is a which is one of the deep neural network, which can be used to enhance the image, underwater image. So this is what we have implemented. Thank you.